I'll start with Metropolis hashings as the most generic method to do Markov chain Monte Carlo, with, again, no intention at being advanced or deep, but just giving the idea on what Metropolis hashing is. And of course, feel free to interrupt. You want it broader, yeah. That's it. Okay. All right, so why do we need Markov chain Monte Carlo methods? It's because previous Monte Carlo methods were unable to deal with certain integration or exploration or optimization problems. We're either unable or too slow or too inefficient. And the realization that is at the basis of Markov chain Monte Carlo methods is that to approximate, say, an integral that is connected to a certain distribution f, we don't need to simulate from that distribution f. We already know that if we know about importance sampling, that importance sampling allows to simulate from another distribution and then to switch the integral against that other distribution. MCMC goes another path, namely that if we can produce a Markov chain that converges to f in the ergodic sense, then it's enough to produce an equally convergent approximation to this integral. And so that's the fundamental idea behind MCMC method. So the idea is to try to produce such a Markov chain, xt, that is ergodic, so converges no matter what the starting point, and converges to a certain distribution f, that is the distribution behind the integral we try to approximate, and more broadly, that is, in Bayesian statistics, a posterior distribution that we try to learn about. And so to implement this idea, we need a Markov kernel that will be connected with f and will produce an ergodic Markov chain. Okay, so that seems a bit formal, but actually there exist generic solutions. And if we have such a Markov kernel, and we can implement it on a computer, we will produce a sequence of numbers that will constitute a Markov chain, which will be used to get to a maximum connected with f, or to approximate the integral, or simply to represent this complicated target, the distribution f. Okay. And so those are some notions that we can use from this Markov chain, namely that if t is large enough, so after a certain t naught, xt will be simulated from f, either approximately or exactly, depending on the method. And more useful to our goal, the sequence xt naught, say xt naught plus 1 and so on, will be a sample from f with the drawback that it is a dependent sample and not an IID sample. Okay. And then we can explore more the properties of this chain, but the starting issue is how do we build a Markov chain that is guaranteed to be ergodic against a given distribution with density f. And the Metropolis hashing algorithm is the answer to this question, or a answer, but it is the answer in the sense that it can produce such a chain almost automatically. So what it requires is the target distribution with density f that at this stage needs to be known up to a multiplicative constant, which is exactly the setting for Bayesian statistics. You are given a prior and a likelihood function, and assuming you can compute numerically this likelihood function, then the product is known. We are missing the normalizing constant for this product to become a density in the parameter, but for our purpose, that's not needed. In the event the likelihood is not available in a numerical sense, that we cannot compute the likelihood function for a given sample and a given value of the parameter, then we need more advanced techniques that are either demarginalization, that we need to introduce auxiliary variables, or other techniques like ABC that Jean-Michel will present in a few minutes. So that's a given that we try to achieve simulation from this target. And then the second step is to choose another kernel that is available, that can be computed, and that can be simulated. So this Q is a free choice that we will pick to simulate effectively values that should converge to F. So F, we don't know to simulate from. It may be very complex in a high dimension with all kinds of complications. And Q is a parameter of the algorithm that we call the proposal in most cases. Okay, and that's all we need to run this algorithm where the Markov chain is in state xt at time t, and to create state xt plus 1, we first simulate from this distribution that we picked, the Q of y given xt, the Markov kernel that we can pick as we wish. And then, because it is not connected with F, we need an extra step to make it connected with F. And that's the acceptance step of Metropolis testing, namely that this yt is either accepted or rejected. If it is rejected, we reproduce the current value of the Markov chain. It means that we explored a point that is not so interesting. But if we accept, we just take xt plus 1 equal yt. And the magic of the algorithm is in picking the probability alpha or rho of acceptance in this algorithm. And rho is connected with F. That's where F appears. It is a ratio of f of y over f of x. So y is a new value. So how likely is it compared with x in terms of the target? And then there is a correction for using Q, which is the inverse ratio, Q of y given x over Q of x given y, which is what we actually use to simulate the y. Okay, so we have this ratio f of y over Q of y given x, which is what we would like to use over what we effectively use. And, well, because it is a probability, we have to truncate this ratio at 1, which doesn't matter for all practical purposes. Okay, so, I mean, we could talk a long while about this algorithm. It is very basic in that all you need to know is f up to a constant, and then you have the choice of this kernel Q that you can implement on a computer. As I mentioned earlier, f doesn't require a normalizing constant, so that means that we can multiply f by any constant. The algorithm remains exactly the same. But we have the same fact for Q, that we don't need a normalizing constant for Q, and in some cases that's an advantage. In spatial cases, when Q is symmetric, this ratio cancels, it's 1. And so there are cases where we don't need to know Q at all. All we need to do is simulate from Q. And again, there are cases where it is a big plus. Okay. Now, because f is involved, we can never move to a value of y that is impossible for f. So if f of y is 0, we automatically reject, which doesn't mean we shouldn't propose value of y that are such that f of y is 0. If the support of f is complex, there is an advantage in simulating from time to time values of y that are known to be outside the support, because that makes for a wider proposal, and that may be an advantage. Okay, so for instance, if you truncate a positive random variable, you may use a normal proposal that will be sometimes negative, and that's not prohibited by the algorithm. It's just that those negative values will be rejected, and therefore we will repeat the previous value. So that's a very specific feature compared with other methods, namely that xt may appear several times in the simulation. So we are simulating from a continuous target, say continuous against the Lebesgue measure, but still in the sample we may spot, or we should spot actually several times, identical values. And it's because we are simulating a Markov chain, so the sample is dependent, and there is a positive probability that you observe several times the same value. So it's not incompatible with simulating from a continuous target. It's simply that the Markovian nature of the algorithm means a possible repetition in the simulation. And the last point that is not of direct interest, except if we do Rao-Blackwellisation tomorrow, is that yt, so the sequence of simulated values, itself is not a Markov chain. It associated with xt, it constitutes a Markov chain, but by itself it is not. It's more of an HMM, if you want. Okay, so the first question is, why does it work? Well, it's just a one-line reason, namely that the Gibbs Metropolis kernel, K, which is made of the simulation and of the accept-reject steps, this kernel has this so-called detail balance property that f times k in y and x is equal to f times k in x and y, which means that if you integrate out both sides of the equation in x, on that side you get, if you integrate in x, you get f of y. If you integrate that side, you get the distribution of the chain after one step, assuming we started from f. And so because f of y is the integral of this quantity in x, it means that f is indeed stationary. If we start with the distribution f, after one step, we are still distributed as f. And of course, after any number of iterations, we keep being simulating from f. Okay. So it cannot be simpler than that. The chain enjoys f as its stationary distribution, assuming, of course, there is a possibility to go anywhere. So the chain, assuming that the chain is irreducible and doesn't stick to regions of the space, because otherwise it would mean that restriction of f to those regions are the stationary distributions. Okay. So, I mean, it's a neat proof, but you have to assume a bit more that the chain can go everywhere. Otherwise, the restriction of f becomes the stationary distribution. Okay. And then from those properties, we derive immediately that the chain is positive recurrent, so we don't have to prove much more. And then the last point is that the chain may be periodic if we are very unlucky. But if there is a certain probability that the chain sticks to the same value, so if this has a positive probability, then this may happen once, twice, or several times, and therefore the chain is aperiodic, which is a minor property anyway. But so if we have those three properties, we have that the chain is converging, not only stationary, but it's also converging to f no matter what the starting point, or for almost every starting point, the chain will converge asymptotically to f as its distribution. Okay, so those are more properties. Irreducibility, again, is an important issue that is not always easy to check. One easy requirement is that Q is everywhere positive on the support of F, in which case irreducibility is guaranteed, but that's not a necessary condition. You may have Q positive on a compact set and still get irreducibility. Okay, let me skip those conditions. So, very quickly, a comment is that you can connect this algorithm with either accept, reject, or important sampling. Namely that if Q is independent from X, so if it's not a Markov kernel, but simply a certain density, G, then you generate from this proposal all the time. So you generate a million simulations from G, and you keep those that fit this acceptance step. Otherwise, you keep repeating X. So it's still a Markov chain despite simulating from G. And it's not theoretically, it's an interesting algorithm. In practice, it's really interesting because you have to imagine a G that fits F enough, and so it has essentially the same drawbacks as accept, reject, or as important sampling that F and G has to mimic one another. And so if the target is complicated, or if you are in large dimensions and the curse of dimensionality hits, it's almost impossible. So you can prove a lot of things, but not much in practice, except in some area where it's useful as well. Okay, so I'll skip that. To move to the most generic of the Metropolis hasting algorithms, namely the random walk proposal, which makes a lot of sense when you are facing a complicated target, a complicated F. You don't know where the regions of high probabilities stand, and so you are blind and you look around where you are. And so the notion behind the random walk proposal is that you are somewhere with a Markov chain and you explore a certain neighborhood of this current value. And if you're lucky, you will hit another point that has a high enough density and you'll move there. If you're less lucky, you'll hit something with probability 0 and you'll try again until you keep moving. Okay. And so you could do all kind of exploration centered around xt. The random walk has the additional requirement that the proposal is symmetric around xt, which leads to this simplification in the Metropolis hasting ratio, that the ratio only depends on f, no matter what q is. So you could make a proposal from a normal centered at x, but also from a Cauchy centered at x, or any symmetric distribution that is centered at x, a uniform, for instance, that would work as well. This doesn't appear in the ratio. Of course, it impacts the convergence properties of the algorithm, whether it's fast or slow, or whether it's reducible or irreducible. But in this acceptance, you only look at f. So you keep moving, provided you go higher on the surface of f. And sometimes you move if you go lower, which is a strength, because then you can skip from one mode to another, okay? Provided you have enough energy to jump between modes. And so just a toy example to see how it works. I created this silly target, which is called pi instead of f, by multiplying a normal density with two square sinuses. And my proposal, my Q function, is a density of a uniform kernel that is centered at x. Okay. And so I generate a uniform between -1 and 1. I add it to my current value of x, that is theta in that slide. And I move is another uniform is less than the ratio, which is pi at the new value over pi at the previous value. Okay, that I wrote as a posterior, but that's exactly what's represented here. So I will move if I go high enough, and otherwise I will stick to the current value. Now, there is an alpha that I have to pick in this algorithm, as an example, and that's characteristic of random walk proposals. The scale of the proposal can be chosen between 0 and infinity. So in theory, it should work for any alpha, but we choose the alpha so that the chain moves at a reasonable rate that I will mention later. So good doesn't mean close to 1 in that case, but rather close to 0.234. That is a magic number for the random walk MCMC. Okay, and so that's very easy to implement. So that's my R code. I start from a purely random number, 314, and then I run this 10,000 times. Okay, so and I get this outcome after 10,000 iterations. The histogram against the target has visited the 4 modes of the histogram. Again, that's a toy problem, so it's not a major victory, but in that example, it works. Okay. And of course, so I started from pi as my beginning value, but this was my chosen scale 1, and we'll see examples later that this has an impact. Okay. So in terms of properties, actually you can prove less for a random walk than for the original independent proposal because it's local. So since it's local, you cannot get very good properties in the sense that if you start in a terrible region of the space, it will take you some time to get away from this terrible region, depending on the scale of your walk. I mean, you do a random walk, so you have to go there by foot, and so it takes some while, okay, even if you're running. So the best case is that your chain will be geometrically ergodic, but it cannot be uniformly ergodic unless you are on a compact space. Okay, so that's one of the properties. Okay. And so to just represent the difference between geometrically and not geometrically ergodic, I don't know if you see much, but those are 2 envelopes for 2 cases, one that is geometrically ergodic and the other one that is not. You don't see much of a difference, and there is not much of a difference indeed in that case. But of course, this may slow down. This I'll skip. I think I'll skip all that. To move to some of the extensions. So again, if you have no idea how to run your MCMC, the random walk is your off-the-shelf solution that you can implement in many ways by choosing different parameterization, different proposals, and mixing all of them. The more, the merrier. You get at least the speed of the best. And so among metropolis testing or testing metropolis algorithms, there are other specific proposals. One of the earlier ones was adaptive rejection metropolis sampling. So this was the proposal at the core of the bugs software, which was working somehow off the shelf without any calibration. And so it was a mimic of accept reject with the metropolis step. It's no longer the basic proposal because it doesn't work very well. It requires small dimensions, so it doesn't work very well. Reversible jump is another specific case that takes too much time to explain for me to cover it, but it's a proposal that works in spaces that have different dimensions. So your target is a vector of varying dimensions. Actually, the dimension of your vector is one of the things you don't know. And so you move among spaces that are of different dimensions, and this requires a bit more care in terms of measure against which measure do you simulate. And Peter Green's reversible jump is one solution to this. And then Langevin I will mention in a minute. The last one is Hamiltonian Monte Carlo, which is a method that came from physics that is not traceable, that goes against the random walk proposal to avoid wasting time going forward and backward. That I will not cover either, but that's more of the state of the art in some sense. So if I may mention Langevin, the Langevin algorithm is based on the Langevin diffusion. That is a continuous time process that enjoys f as its stationary distribution. So if you define the diffusion against the Brownian motion and this drift that is induced by the target f, then it will correspond to f as its stationary distribution. Of course, it's continuous time, so I don't know how to simulate in continuous time. So I simulate in discrete time. I do a Euler discretization. And I get this move that is very similar to the random walk move, except there is a drift that is induced by the log of the target. And then we have the choice of the discretization step that turns into a scale for this move. Okay? So we have a Markov chain that moves according to this. And so that's the discrete side of the continuous diffusion. So that could solve all problems at once. We would have a Markov chain with f as its stationary. Unfortunately, that doesn't work so nicely because the discretized version may have very poor properties. For instance, it may be transient. So it may go up and up and up and never come down to a region of interest. And so we need to correct for this Euler discretizations. In some cases, you can prove that the chain is correct, but often it's too much work when f is a complex target. And so there is a Metropolis correction to the Langevin diffusion, which leads to this algorithm where you propose according to the Langevin step, but then that's a proposal like any other. Therefore, you correct it with a Metropolis-Hastings acceptance probability. Okay. And so that's the acceptance of the new value. Of course, the proposal takes more from f, so it usually has better properties than the basic random walk Metropolis because there is a pull towards the high values of f. So the modes are more attractive than the random walk that is totally blind, or at least myopic, and goes around totally with no knowledge of f. This may be a drawback if your target has multiple modes, because then you need to jump from one mode to the next, and the local mode may be too attractive. And so that relates to the choice of the factor sigma. If it's too small, you may get stuck to a local mode that you know very well, but you totally ignore other modes. And so there is another magic number for Langevin Metropolis-Hastings algorithm, which is 0.574, which gives an idea on which acceptance rate we should aim at to run the simulation. So just a few words about this. The Metropolis-Hastings algorithm is quite generic in that it theoretically works no matter what your proposal Q is. And you have to simulate on the same space, of course, but essentially you have very few restrictions. Now in practice, very quickly you realize it doesn't work if you pick the wrong Q, that is something that is unconnected with F. And so there is a problem of calibration of the algorithm. And one of a few basic ways to calibrate your proposal is to look at the acceptance rate because it tells you something of the performances of the algorithm. That is, if it is very large, very close to 1, it means that you accept all the time. And so you keep proposing values of f that are very high. Otherwise, you would reject. If it is very, very low, if it is 0, it means you keep proposing values that are not acceptable from f. So you simulate in regions that are not interesting. And so you need to do something, because if you don't move, it's very unlikely that it will converge anywhere. Okay? And so in some cases, you have to look at very high acceptance rates. And this is the case for independent Metropolis hasting. The higher, the better. It's like accept reject. The lower the bound, the better. But again, that's a very specific case that we don't meet very often in practice. In the case of the random walk, the intuition is quite different in that, remember, we are exploring locally. And so a high acceptance rate means that we may be too local because we don't see often enough low values of the target, which we are still interesting, and also which may hide further values that are further away with high probability values. So again, it's a way of multimodality. If f is multimodal with high acceptance rates, we probably miss the other modes of the target. And so we have to aim at lower acceptance rates, not too low, because otherwise the chain doesn't move fast enough. Eventually it will get there, but maybe not in human time. And so there is a theoretical study that leads to a rule of thumb devised by Gallman, Gibbs, and Roberts, which is this 0.234 magic acceptance rates. And just to illustrate the role of the alpha in my sinusoid Gaussian example, if alpha is 0.25, after the same number of iterations, I get this histogram for my Markov chain, which means I missed two modes that are here and there. Okay, so 0.25 is a bit too low to have the energy to jump for my chain to jump from that mode to the next one, which is invisible, and which in complex problems I would not realize is there. So that's one issue. And if I move to even lower probabilities, which is a scale, sorry, so very low scale, means that I started from pi, and I am stuck with a very low mode, because it's low enough so that the target is this blue line. Okay, so it's unrelated to the target. It's just a small bump, but the chain doesn't have the energy to jump to the next mode. Okay. So that's one issue. And that's another example of noisy AR, where I simulated 100,000 values from a certain target, that is this orange line, and it fits beautifully the target. And you can see that the chain moves, sometimes gets stuck, but moves. So if you only look at that, you should be very happy with the performances of your algorithm. So there is a scale that is 0.1. But if I move to a scale of 0.5, then the chain doesn't look very, very friendly, because it sticks, and then after a long while it moves, and then it sticks again. So if you look only at that, you would think, well, let's get rid of this algorithm. But actually, in that case, we have the same target, and then we get a new mode that is higher, and that is a region we should have explored. So with a larger scale, well, we don't have a very congenial Markov chain, but it does the job that the previous one missed, while moving more, but missing the other mode that is somewhere here. Okay? Okay, so this is a very quick introduction to Metropolis hastings. And again, I will talk about it in another way tomorrow. I want to mention Gibbs sampling. Well, it is somewhat a special case of MCMC, maybe a too special case. It has different appeals. The first one is that it borrows more heavily from the target distribution, and so it should have better properties, which is not a sure thing. The second thing is that historically it came in a different path through image analysis, and so there are different notions to the Gibbs sampler compared with Metropolis hastings. And the third reason is I really want to mention the Hamiltonian-Clifford theorem. So what is different from regular Metropolis hastings when you run Gibbs sampling? It is that you start from your target that you cut into slices. So you are in dimension whatever, you decompose your vector into subvectors, x1, x2, xp, for which you can simulate the full conditional densities f1, f2, fp, which means that you can simulate from fi of xi given the other components x minus r. Okay. So the assumption is that we have a target that is in a maybe very large dimension, that is too complex to simulate directly, but for which we master the full conditionals. So that means essentially that maybe we can write numerically the value of f. If we fix everything but xi, we have up to a constant this fr. Okay. And so we can simulate from fi, or if we can't, we can run one step of Metropolis hastings to simulate from this fr. Okay. So the primary goal is to deal with large dimension parameters that are the component of x here, by going small, by doing one direction, one dimension at a time. So it takes longer because you have to go around the clock many times, but it simplifies the simulation, and because we simulate from the right conditionals, we have a guarantee of convergence, or at least of stationarity as well. Okay. So the algorithm is just to run through the components of this vector, simulating from the true conditionals. Therefore, this produces a Markov chain that converges to f by a very simple reasoning, namely that if you are in the stationary distribution, and if you do any of those simulations, because you use the right conditional, you stick to the same stationary distribution. Okay. Then it has properties that differ from regular Metropolis hastings. For one thing, you don't have rejection. You keep accepting, so the chain keep moving, which is not necessarily a plus, because rejecting may create better moves. But for simulation reasons, that may be an interesting thing. The chain is not reversible, so the order in which you explore the vector has an impact on the convergence properties, which mean that it's better to do it randomly, so that the order doesn't impact the performances. You get the best performances by doing it random. Doing the double sequence is not that great, so I wouldn't advise it. And so, where is the difference? Well, it says that by using the conditionals, you have to follow the patterns of the target that may slow you down. So here is an example where it's not the case. That is a Bayesian posterior on mu and sigma square, where, well, we know the posterior, that's a toy problem, but so mu is a normal, sigma square is an inverse gamma, and so we can simulate each of them at a time. Again, the code is straightforward. And so it goes like that, and you see it goes either horizontally or vertically. So if there are strong boundaries that you cannot avoid, that puts a strong restriction on the moves of your Gibbs sampler. And so that may be the difficulty, and the larger the dimension, the more constraints you have, and so the longer it takes to go from one end to the other end of the target. Of course, here it's pretty symmetric and unconstrained, so it works nicely. Okay, so it has some restrictions. You need to know something about F. If F is a black box, that's more complicated because you cannot simulate directly from the conditionals. You have to use a Metropolis Hastings step to replace the simulation, but just one step, not a full simulation. You need to be able to compute F to some extent. It is multidimensional, but we will see an answer to this problem. And then it's very hard to extend Gibbs to problems where the dimension varies, because if the dimension is one of the parameters, as soon as you condition on that dimension, you are stuck in this space. You cannot change the dimension. So there is no version of that. Let me skip that. Oh yeah, just an example where it may get stuck because of the structure of the space. So I have a target that actually is a posterior distribution for a mixture distribution that has two modes. One that is around the true value of the parameter, which was 0 and 2.5, and another one that is a sort of atavistic mode due to the mixture nature of the likelihood. If I start at random, that's how my Markov chain produced by Gibbs converges, so it goes to this mode and stays there forever after. However, if I start from the other mode, and here I had 100 observations, so it's a fairly peaked likelihood, the Gibbs sampler by itself doesn't have the strength to pass here, to pass this saddle, so to go down and up again. So if I run it for millions of iterations, it will never leave this mode, which is, again, much lower because this is a log scale. The two modes are quite different in that problem. So that's the difficulty with using the full conditional, that you are heavily constrained by the nature of the target. And usually, because of the dimension, it's long or even impossible to move from one end to the next. Now, about the dimension, there is a way around this difficulty with a small dimension, or dimension 1, which is namely that you can produce a quasi-generic Gibbs sampler, just like the random walk Metropolis Hastings is a generic Metropolis Hastings, by the trick of slice sampling that apply in principle to any problem. If your target f is a product of other functions, fi, and let's assume that the fi's are simpler and known, again up to a constant, then this fi is the integral of this indicator. If I integrate this indicator in omega I, between 0 and fi, I return fi. Okay. So this product is the marginal of that product of indicators. And so if I have trouble simulating from that product, maybe because there are too many FIs or they are too complex, I can take them one by one, and instead of simulating from the product, I can look at this new distribution of theta plus omega 1, omega 2, omega k. So I just created, out of the blue, a new distribution in a larger space, but that is a uniform distribution. Okay? Because here I only have indicators, so my density is 0 outside and 1 inside. which is a definition of a uniform density. Okay? And I can run a Gibbs sampler, naive Gibbs sampler on that new target, which will be proportional to the indicators, and therefore which will be uniform again, but one dimension at a time. So I generate these different uniforms, and then for the omegas that have been introduced just for the purpose of the simulation, and when I meet my theta, then I still have a uniform, but over that set, which is the intersection of all those constraints, which is where things may get a bit difficult, because this set may be too complex to produce a uniform. Then we may need another Metropolis step to explore that step. But that's to say that you can run a slice sampler almost automatically in any problem, and therefore a Gibbs sampler, which is a default solution, if you wish. And depending on the nature of the region where you simulate this slice sampler, so here I took the tail of a Gaussian, the exploration is actually quite efficient and has good theoretical properties, because you can, if you don't hit a corner or a gap, you can go essentially from anywhere to anywhere in very few steps, as illustrated in that example. You can prove some properties like even uniform ergodicity, which was not the case for the random walk. Okay. Yeah, well, the properties, I mentioned them already. So it can be uniform. Let me skip that. It doesn't work all the time if the slice. This is an example of Gareth Roberts and Jeff Rosenthal of a normal, an L1 normal in dimension D. So you use the L1 instead of the L2 norm, and this is essentially like simulating from this target in dimension D, U being the radius. And if you push D to 100, you get something that is very, very flat. And if you use a slice sampler in that example, you get enormous correlations. And so it takes forever to explore the space. Okay, so I wanted to mention that just for the sake of it. There is a justification to Gibbs sampling, which is the Hammersley-Clifford theorem, namely that if you have a collection of conditionals, you can recover the joint. So for instance, if you have only two components, and if you know both conditionals G1 and G2, the joint is given by this ratio. So if numerically you can compute G1 and G2, then you get the joint. And there is a general version of that theorem, which is that up to a constant, the joint is given by a ratio, a product of ratios of full conditionals, where y prime is any arbitrary fixed value. Okay. And that's interesting not only because it explains theoretically why, if you know only the conditionals, you actually have the knowledge of the joint, but it's also interesting because it connects with some acceptance probability that you could have produced by Metropolis Hastings. Okay. Now, this theorem was never published by Emerson and Clifford because the difficulty is that this ratio requires the denominator to be positive, so that's what's called the positivity conditions. And in cases where the support of the joint is not the product of the supports of the conditionals, the theorem doesn't apply. And so they got unhappy with this condition. And it's only Julian Bizag later that published a version of that theorem. Just a few words on Rao-Blackwellisation, because presumably I will talk about that tomorrow. once you produce your Markov chain, there are post-processing steps that help improving the estimation of integrals. And Rao-Blackwellisation is one of them. That when the chain has been produced, you are in the stationary distribution, but if you want to approximate a certain integral, you can do better than take the average by recycling more of the simulation than just the raw output. And so, for instance, if you have in a Gibbs sampler several components, but you are only interested in the first one, assuming you can manage this conditional expectation by Rao-Blackwell or Jensen or just a conditional expectation argument, this conditional expectation has a smaller variance than the original one. And assuming the correlation doesn't get into the way, this estimator will have a smaller variance. Okay. So in some cases, you can produce much more stable estimators by Rao-Blackwellisation. And there is an illustration that is important in Bayesian statistics, that is Gibbs' method for approximating the base factor. It is essentially a Rao-Blackwellisation argument as well. Okay. And then also, Rao-Blackwellisation can be used in a non-parametric way, which is that if you are interested in one marginal posterior distribution, gi of yi, for instance, the full conditionals averaged converge to this at a parametric speed. So you can produce very accurate or more accurate than non-parametric estimates of some of your marginals. And then last point, a warning that is only applicable to Bayesian statistics, namely that if you use improper priors in Bayesian statistics, that doesn't prevent you from using MCMC. However, you may fall into the problem that taking the product of your improper prior, say a flat prior, and your likelihood, you're able to define well standard conditional distributions for all your parameters, therefore simulate from those, but produce a Markov chain that has no stationary distribution because the joint distribution that comes with those conditionals does not exist. This is connected with the fact that the posterior distribution doesn't exist and the fact that the improper prior has an infinite mass. Okay, so this is a danger, and it's quite a danger in the sense that these conditionals are perfectly valid distributions. So just a toy example from Casella and George, where if you take the joint that is exponential x1, x2 on R plus, this joint is not a probability density because its mass is infinite. However, if you take x1 given x2, derived from this, you get an exponential x2. Same thing for x2 given x1, you get an exponential x1. Okay. And so the Markov chain that you will create using those two conditionals via a Gibbs sampler will have transient behavior in that it will take larger and larger values and then smaller and smaller value and have wider magnitude as you proceed. Okay. In that toy example, you will spot the difficulty very, very quickly and realize there is a problem. In more complex models, it is not so obvious. So here is an example with random effects where the full conditionals are very standard distributions. I use an improper prior that is Jeffrey's prior. And so if I simulate from those four standard distributions, I get paths like this and histograms like that, which do not tell me anything is wrong. However, something is wrong because you cannot integrate in tau this joint distribution. And so you get an issue that is not spotted by the output of the Gibbs sampler, because the difficulty is very close to 0. So in a sense, your machine precision prevents you from spotting the difficulty. But from a Bayesian point of view, the posterior doesn't exist, so your output has no precise meaning. And so this was published in one of the first Gibbs paper. Okay, so the warning that if you use an improper prior, pay attention to this issue, because it's not so current or common anymore, but in the first years of MCMC, a lot of people spent a lot of time trying to debug their code without realizing that the issue was not the code, but the prior. Okay, it's 10, so I think I'll stop. 5 minutes? Okay, then I won't stop. I just have 100 left, so it's fine. So the last part in this section was about sequential importance sampling. So it seems like going to another domain, but actually it's very connected with MCMC. And I presume I won't have time to reach pseudo-marginal, but I will talk about it tomorrow. So it's another warning, which is that when you start on a new problem, if the target is really complex, you have no idea how to build your proposal. And Gibbs sampling, Metropolis may give you some idea where important regions are, but not globally. So one natural suggestion is to try to keep changing algorithm as it proceeds on the target so that it works better. For instance, aiming at this 0.234 acceptance probability, or changing the variance in your proposal if you are in a high dimension, modifying the order of the simulations, and so on. Or even using a non-parametric estimate to make a new proposal. Now, if you do that naively, you create an algorithm that is not an MCMC algorithm any longer, because your chain, or your current value, depends on everything you saw before. So the dependence is extreme, because it's built on everything you saw. Okay, so it's not a Markov chain. And so to show you, again on a toy example, what can happen, I took a T distribution as my sampling distribution, and I'm interested in theta. And so my target has this shape. It is mu plus x minus theta squared to the power, product over the sample. So it's the inverse of a polynomial in theta. It's not that complicated. And let's say I run a random walk Metropolis testing where I adapt the mean and the variance from what I've seen. It should be fine, because essentially this should converge to the right mu, and this should converge to the right sigma square by ergodicity. So I create a normal independent with mean mu and variance sigma square, except that I use a past of my Markov chain to estimate this mean and this variance. And again, this was a standard suggestion in the early years. And so what happens is that if you run it, even with a certain burn-in stage where you learn with a fixed value of mu and sigma, it doesn't work. It doesn't work because it keeps concentrating on wrong parts. And these are 3 examples with a certain initial variance. So if it's really too small, it just get mirrored or stuck in the initial region. It just cannot get away from it. Even with a large variance, there is a gap that doesn't disappear because it's just too slow to move around. As in this example. And then I run also the attempt to use the past to build a non-parametric estimate of the target. We're in dimension 1. And even there, it has too much of a memory of the past to be ergodic to the right target, as you can see there. Okay. So one advice is just forget it. Another one is to just be practical. Use a first simulation run to build a better proposal. Use that proposal and run a second set of simulations until you're happy with the performances. Or be very careful and use adaptation methods that are less and less adaptive. So the memory of the past kind of vanishes at a certain rate. And so, for instance, Jeff Rosenthal has an R code that does that with decaying adaptation so that it's guaranteed to converge. But essentially, you have to set your algorithm more and more as time proceeds. Otherwise, you cannot prove that it will converge. Okay, I'll stop here.
So thank you, Christian. Are there some questions or remarks?
A big issue, like always, is... okay, so a big problem with MCMC and with any other scheme to approximate the posterior is always when we have multimodal targets, as you showed in multiple examples. And just, do you have any recommendation for like what you would do on when you have a multimodal target to, I don't know, detect that multimodality or handle it in some clever way?
Yeah, so three ways at least. The first one is try tampering. So try to set your target to a power less than 1. As the power decreases, the target is flatter and flatter. And therefore, if you run a Markov chain with a given energy, as it gets flatter, the chain will move better. And you can learn the modes through that type of exploration, but also you can incorporate it into a perfectly valid MCMC, like in parallel tampering. So that's one solution. A second solution that is a form of tampering is sequential exploration. That is, if you have a posterior distribution, you start with a few observations, you run your MCMC, and then you keep adding observations, and then it will get more peaky, but then you will know where the regions are. So that's another way, which is a form of tampering inspired by the likelihood structure. And the third solution is to try reparametrization. That is, if you modify the parametrization of your model, like if you bring it back to a box, for instance, an hypercube, the performances will be different. So if you accumulate different parametrization, this will make different proposals, and you may hit a mode that way. But of course, there is no foolproof solution. That if the mode, like if the Mexican hat far away, there is always a chance you don't hit that mode. Yeah. But reparametrization, I think, is one of the ideas I'd be interested to implement to solve this kind of problem, if I knew nothing better. Yeah.
Okay, is there any more questions?
It's very generic. Just if the slides will be available after the course.
So the slides are available on the same depository, SlideShare.
All right.
Yeah, they're already there.
Oh, perfect. Yeah. I didn't see. Thanks.
But otherwise, I mean, the slides are on my homepage because they are essentially my MCMC course slides. So.
Great. Thanks.
Yeah, good morning. Please share your affiliation detail. I would like to, your affiliation detail and contact detail.
Oh.
Your contact detail, I would like, yeah, thank you.
Yeah. I'll be here all week anyway, so. At least until Wednesday.
One more question. So thank you, Christian, and there is a coffee break now.